we'll move along. So let's begin. So on Monday, can you all see that? Yeah, maybe. Okay, so on Monday, we talked about this idea of measuring the shape of mathematical objects. So and perhaps when we say measuring the shape, we mean perhaps surfaces, right? Like perhaps a disk or an annulus. Or we mean the shape of a data set. You know, perhaps your data set is just a collection of points in some Euclidean space. So the first idea of how to measure the shape of a surface was this idea of triangulating it, right? So what you did is you picked perhaps some vertices, and you drew some edges dividing your surface into triangles. And let's do that. Let's do the same thing here. And then the thing that we talked about last time is that once you have your surface triangulated, you can compute things like the Euler characteristic. So let's do that here. Which was this number chi equals to the number of vertices minus the number of edges plus the number of triangular faces. Correct? And then if this is the disk again, if this is an annulus, then what one can compute is that the Euler characteristic of the disk is 1, the Euler characteristic of the annulus is 0, and since this number does not depend on sort of continuous deformations of the space, then we conclude that this space cannot be deformed continuously into that space because they have different Euler characteristics. Okay, so that was sort of the first idea of how to measure the shape of a surface. The second idea we used was if I give you a data set, which is just a collection of points, then what your brain tries to do is sort of close the gaps between the points. And one way in which one can formalize that is saying, you know, if I have, let's say, a tolerance epsilon, then I can join with an edge every 2 points that are nearby, let's say at a distance less than epsilon. And, you know, perhaps these 2 points also have an edge between them. And the idea was that if you have 3 edges, then we fill in the triangle. And if you have sort of 4 edges, you have all the edges connecting 4 points, then you fill in the tetrahedron and so on, right? So measuring shape for surfaces with the Euler characteristic and measuring the shape of data sets via this construction of building triangulated spaces using distances, okay? So what I would like to do today is I want to formalize this idea of triangulated spaces. And the concept is that of simplicial complexes. By the way, everything I'm going to say today can be found in chapter 1 of Moncrief. So it's one of the books I suggested as reading material. So simplicial complexes are going to allow us to formalize sort of this idea of a triangulation on the one hand, and they also will allow us to create algorithms to measure shape using computers. So let me start with the definition. So I'm going to let, since I have vectors u0 through uk in Euclidean space Rd, then these points are said to be affinely independent if, let's say, u0 minus u1, u0 minus u2, all the way up to u0 minus uk are linearly independent. Okay, so is the idea that, right, so for example, 3 points, so for example, if you take 3 points on the plane, then them being affinely independent means that if this is, let's say, u0, this is u1, and this is u2, then these vector and this vector are linearly independent, meaning that they are not in the same direction. So these guys are affinely independent. But for example, these 3 guys, u0, u1, and u2, are not, because they are sort of on the same line, right? So affine independence is sort of that they sort of span sort of a non-degenerate space. I'm going to make that more precise in a minute. Okay, so that's what being affinely independent. And when I say linearly independent, I really mean in the linear algebra sense, that there's no non-trivial linear combination of these vectors that gets you the 0 vector. Okay, so the second definition is that of a geometric simplex. So given k plus 1 vectors in Rd, which are affinely independent, the geometric K simplex spanned by u0 through uk is the set u0 through uk. So it's the collection of affine linear combinations that look like this. So j from 0 through k of lambda j u j, where hi. Did you call for I did, yes. So we just want to sort of record. I want to record my voice without it sounding in the speakers.
And what device are you recording with?
Just with it to the computer.
And okay, so you should be able to, as long as you don't mute it. You're not going to be doing 100%, but
okay, and then does it work? Okay.
So as long as you don't, now it's not working, right?
I mean, it's responding here, so I imagine this. So now it's not working.
Okay, as long as you don't mute it.
It should work?
Yeah, I can't make it 100% gun, but at least you won't be so loud.
Okay, let me try that.
Yes. And can you test, or do you want me just to go? And
yeah, we'll see at the end if it worked.
Okay, so I just got the call, so I don't know when you called it.
Yeah, I don't know. That's fine.
So
okay.
As long as you don't mute it, it should work.
Okay, we'll see. We'll find out at the end.
And you're on right now?
Yeah. Yeah.
There. Okay.
Okay.
Call back and we'll work it out if we have more time. You know what I mean?
Yeah. Thank you.
Sorry. Have a great day.
Okay. Sorry for the interruption. So where was I? Yes. The geometric K simplex spanned by these vectors is just going to be the collection of linear combinations that look like that, where the lambdas are non-negative and they add up to 1. Okay, So that's the geometric simplex spanned by these vectors. And here are a couple of examples. So let's take, for example, u0 to be the vector 0, 1. And let's let u1 be the vector 1, 0. And this is going to be in R2. Okay? So here is u0, and here is u1. Then the geometric simplex spanned by these two guys, this is going to be the set that looks like, perhaps it's just easier to say u0 times t plus 1 minus t times u1, where t is between 0 and 1. Correct. So it would be just the line joining these two guys. Okay. So this is called a geometric, so this is the geometric 1 simplex, which is spanned by u0 and u1. And it is in that sense that I wanted the vectors to be affinely independent, right? So that if you have 2 of those, then you get a line. If you have 3, if you have 3 such vectors, like u0, u1, and u2, then the affine combination should be just the sort of triangular face that you have in here. Okay, and this would be the 2 simplex spanned by those guys. So here's a sort of notational remark that we will use from now on, and is that if sigma is a K-simplex, right? If sigma is a K-simplex, then we will say that the dimension of sigma is K. It's sort of the geometric intuition. I just want to remark that there are K plus 1 elements in here. And if they are affinely independent, then the dimension of the geometric simplex will be K. Just like in here, you have these 2 vectors, the dimension is 1. You have 3 vectors, the dimension is 2. Okay? The second notational remark I would like to make is that if you have a 0 simplex, right? So it would be the one spanned by just 1 vector. This is going to be called a vertex. In other words, 0 simplices will always call them vertices. If you have a 1 simplex, this is going to be called an edge. And similarly, a 2 simplex is going to be a face, a triangular face. So we will use these shorthands to talk about these low-dimensional simplices. Okay. Okay. So these guys are going to be sort of the building blocks of the geometric objects we're going to construct. So people that are familiar with computational geometry, for example, with modeling geometric objects with simplicial elements, or people that do electromagnetics and stuff like that, are familiar with these notions. So these are going to be the building blocks for the geometric objects we're going to study. So here's another definition. So if J0 through JL is a subset of 0 through K, then we say that tau, which is uj0 through ujl, is an L face of sigma. Okay. And we will denote that by saying that tau is less than or equal to sigma, right? So it's saying that this is a face of this bigger simplex. So for example, so if these two simplex is sigma, then this right here is going to be a one face. Okay. So I guess I'm thinking of this as sigma and this as tau. So you're just choosing L distinct indices, L plus one distinct indices, and you're just taking that subset, and that is giving you a face of the simplex. And now we are ready for sort of the first main definition of the class, which is this. We're gonna have to erase that. Okay, so again, this is going to be one of the main objects we're going to be working with. So a geometric simplicial complex and I would really like to emphasize the word geometric. The reason why everything we're doing right now is called geometric is because we're thinking of points with coordinates in Euclidean space, right? Like things with coordinates. We're gonna move on from that in a moment, but for now, the geometric context is pretty useful to build intuition. So a geometric simplicial complex is a set K of geometric simplices right? So K is just a collection of things that look like this, spanned by some collection of vectors, which is so that if sigma is an element of K, so if I have one of my geometric simplices in K, and so that two things happen. Let me do it here. So the first thing that happens is that if sigma is an element of K, so it's a geometric simplex, and tau is a face of sigma, then tau is also in K. So what it means is that it's closed under the taking faces relation. The second thing I'm going to request is that if I give you two simplices, sigma 1 and sigma 2 in K, then either sigma 1 intersection sigma 2 is empty, or a common face. So I'll explain these two conditions in a moment. So let me draw a picture to sort of indicate what these things are. So I'm gonna draw something that is. This chalk is terrible. We need to chip in and buy high quality chalk. Here, yeah, that's what I was gonna say. Have you guys heard of the story of math professors hoarding high quality chalk, the Hagoromo? Yes, but is it the same company though? I think it's a different company.
Yeah, but it's the same process.
We need to get on that. We need.
It's like $24.
Oh, okay.
I don't have enough coffee.
Okay, we're gonna have to invest in some Huggeroma chalk. Okay, so I'm just gonna draw the picture of something that is. So K is gonna be comprised of the following geometric simplices. It's gonna have a 2 simplex, a 1 simplex here, and perhaps a 0 simplex over here. Okay, so K is just the collection of all these simplices and their faces. So let's call this K prime. Okay. So this is a simplicial complex, a geometric simplicial complex. The idea that, if you write it down, so let's put some numbers to this, so some names to this. So let's call this U0, U1, U2, U3, U4, and U5. And we're going to call these U0, U1, U2, and U3. So K in here is just a collection given by sort of all the vertices. So it's going to be a long list. So U0, U1, all the way up to U5. So those are all the vertices, the 0 simplices. Then the 1 simplices are going to be U0, U1, U1, U2, U0, U2, U1, U3, U3, U4. So I've named all the 1 simplices, all the edges. And finally, I just have to name the 2-dimensional simplex, the face. So U0, U1, and U2. Right, so what do I have? I have all these geometric simplices. Every time I pick a simplex, its faces are also in here, right? We built it from the ground up. But when you look at this guy, the thing that happens is that if you take this 1 simplex, U1, U2, and you intersect it with U0, U3, you're going to get that the intersection is this point. That point is neither empty nor a common face. In particular, it's not a vertex, right? So the second condition here is not satisfied. That's why this is not a simplicial. This is why this is not a simplicial complex, okay? Or at least a geometric simplicial complex. Any questions about the definition? Again, this is a fundamental object that we're going to be using throughout. Okay. Yeah.
Of course, you think that it's simple but complex by actually a number.
Correct, but that would be a different thing, right? So if you were to put this vertex in here, that would be a completely different simplicial complex. It would be a different set. Okay. This is not a geometric simplicial complex, and the reason is because condition 2 is not satisfied. Okay. Yep.
It's pretty clear from the definition,
Mm-hmm.
but not from Apple.
Independent.
But this is all the order-based.
That's a tricky question.
Like the order, like
The indices.
U1, U0, U1.
It is not. It is not. It's the same set. It's the same set because you're going to get the same points when you get the affine combinations, the convex combinations. But I'm writing it with respect to orders for a particular reason that we're going to exploit later, which is called the orientation of the simplex. Okay? So the order matters to me, at least. That's a very good question. Condition is not satisfied? Yeah. So I'm going to take this 1 simplex, the simplex U1, U2, and I'm going to take the simplex U0, U3. Now I'm going to take their intersection. The intersection is this point in here. Okay? Now, is that point, is the intersection I get is it empty? No, it's not. It's a point. Is it a common face? The answer is no, because the faces of, for example, what are the faces of this one simplex? It's this guy and that guy, right? So it's not a common face. Correct. This is an R2. Then it would, and if you were to disentangle it, then yes. Then it would be, if you were to disentangle it in 3D. But the vectors themselves are important, correct? Because if you put it in a different space, you just get a different set. Okay? Okay? Okay, great. Thank you for the questions. So the next thing I'm going to do is define a different notion of simplicial complex. So if I've been going on and on about this idea of geometric simplicial complex, then perhaps there's another type of simplicial complex. And that's what I'm going to do now. So I'm going to define the notion of an abstract simplicial complex. They're both going to be useful. Geometric simplicial complexes are very useful for doing topology, geometry, and having just geometric intuition. But the abstract complex is the one that we're going to put into the computer. So let me just say what it is. So an abstract simplicial complex is a set K where it's a set, let me say a collection. It's a collection K of finite non-empty sets sigma, so that if tau is a subset of sigma, if tau is non-empty, and sigma is in K, then tau is also in K. Right, so what he's saying is that K is just going to be a list of finite non-empty sets, so that if I fix one of those guys, one of those sigmas, and I take a subset that is not empty, then that subset is also in K. These, as we did before, are going to be called the faces of sigma. So this is a face. So we're going to say that tau is a face of sigma. So I'm going to write something down. We'll see what it means. So, so here's an example. I'm going to let K be the collection. So I'm going to fix A, B, and C, just variables, just letters. So K is going to be A, B, C, A, B, B, C, and A, C. Okay? So I claim that K is an abstract simplicial complex. Let's check the definition. So K is certainly a collection of finite non-empty sets. If you take any of these sets, let's say A comma B, and you take a subset, then it can be either AB, A, already here, B, already here, and that works for all the other ones. So every time you take a face, it is also in K. Does that make sense? So for the people, for the Python people in the room, perhaps these kinds of lists make sense to you. Now let's try to make this idea geometric. And the way I'm going to do it is as follows. We're going to say that, so here's sort of a note. If sigma has k plus 1 elements, then we say that it's a k simplex. An abstract K simplex. Okay, so now we're ready to draw the picture. So let's take this set, for example. So this has 1 element, so that means that this is a 0 simplex. So these guys are 0 simplices, and hopefully it's clear that they are abstract simplices. And these guys over here are abstract 1 simplices. For the geometric setting, hopefully we remember that 0 simplices are the same as vertices, and that 1 simplices are the same as edges. So essentially I have 1 vertex per variable, A, B, C, and then I have an edge per set with 2 elements. The thing to notice is that I never decided coordinates for A, B, or C. I never put them in some Euclidean space. They are not vectors. They're just variables. But they allow us to encode sort of the geometric picture of a circle. Okay. So this is how we're going to encode shapes abstractly. Does that make sense? Okay. So what's your name again? Matthew. So Matthew was asking before, how about the order of the vertices? So in geometric land, it is actually useful to have the order to begin with. In here, since these are just sets, they do not have an order to them, unless that you order the variables to begin with, the vertices. Okay, so there is initially no natural order in here, but here we often like to have an order in the geometric land. Okay. So I'm going to write something down now, and you tell me if it is a simplicial complex. So 2. So K prime is going to be the set formed by A, B, BC, and AB. So the question is that an abstract simplicial complex, and hopefully can you draw it? It's certainly a collection of finite sets. So the question is it closed under taking faces? The answer is no, right? Because C is not in there. So not a simplicial complex. So again, the reason is that C, which is a face of BC, which is in K prime, but C is not. So K prime is not closed under taking faces. Okay. Okay, so the next thing I want to do is just a brief comment. I'm going to write it as a theorem, actually. The first thing I want to say is that I never said that K had to be finite. I never said that. So K can be comprised of infinitely many simplices. The simplices themselves do have to be finite sets, but you can have infinitely many of them. So let me say that the theorem is that any finite abstract simplicial complex K can be realized as a geometric simplicial complex inside of Rn for n large enough. Right, so for example, if I give you this abstract simplicial complex, I can certainly come up with a collection of 3 points with coordinates in, let's say, R2, that they are affinely independent, and I can just sort of draw the edges and the vertices and so on. That's what I mean by realize it, to put it inside Euclidean space, giving it coordinates to the vertices. And what I'm saying here is that this can be done in general for any finite abstract simplicial complex. By finite, I mean that this set is finite, that you have finally many simplices. Okay? How do we prove this? Why is this true? So again, remember what it is that you have to do. You have to provide coordinates, affinely independent coordinates for all the simplices in such a way that any two simplices, either geometric simplices, either do not intersect or they intersect in a common face. That's what you have to do to prove that this is true. Yep. Okay, but you do need the coordinates. I really want to emphasize that. Like every simplex has to be a subset of Euclidean space, and the intersections have to be as you were about to describe.
And so basically, any number of intersections,
Mm-hmm.
anytime you have an intersection, if you add the next bit, pull it apart.
Okay.
It won't have that intersection. That's just kind of like
The R3 example.
yeah.
Okay, so how can we formalize an argument to say that? I mean, we wanna write down a proof that this is actually true. So let's start from the beginning, right? So what is the first thing that we should do? We should decide what the coordinates of the vertices are going to be. Okay, so let's start by just giving coordinates to the vertices. And here's one way. So let K0 be the collection of simplices in K that are zero simplices. Okay, just all the abstract sort of vertices. We know that the complex is finite. K is finite. So in particular, I have finitely many vertices. So I'm going to let n be the number of vertices I have, for example. Okay. And what I'm going to do now is I'm going to fix an order for them. Fix an order in K0. So what I mean is that now K0 is going to be, you know, A0, A1, dot, 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 A, n minus 1. Right? So I have n vertices. Okay, now what we're going to do is we're going to give coordinates to these vertices. We're going to put them in Rn. And hopefully you can see where this is going. I'm going to let phi from K0 to Rn. I'm just going to send Aj to the so the jth plus 1 basis element. And this is in the jth plus 1 position. Okay, so for example, A0 goes to 1, 0, 0, 0. A1 goes to 0, 1, 0, 0, 0, and so on. Perhaps a picture will help. So these are the vertices. Oh. Okay. And once you have that, then you can just fill in all the other higher dimensional simplices because these guys are going to be, I mean, they are linearly independent to begin with. So they're certainly going to be affinely independent. Right, so now we're just going to let K bar be the collection of things that look like from J0 to K, lambda J, B of A and J, perhaps. Where to K. Right, so just fill in with convex combinations all the other high dimensional simplices. Right, so for example, if A0, A1 is in K, then you just take the affine linear combination of all these elements. If A1 and A2 form an edge in the complex, then you can just fill that in. That's what this is doing. Okay, so at least you know, we can send it to a perhaps big Euclidean space, right? So if you have a lot of vertices, then the Euclidean space that you're going to end up with is potentially pretty large. Okay? One can actually do better. So the number of vertices seems to be pretty a pretty substantial number. By the way, I'm gonna let you think outside of class why this is a geometric simplicial complex, right? So what do you have to check? You have to check two things. You have to check that all the simplices are spanned by affinely independent vertices. Right? We have that because the vertices were linearly independent to begin with. That is okay. The second thing you have to check is that the intersection of any two simplices is a common face, right? So that's the thing that I'm going to ask you to think about outside of class. By the way, this is save that, save checking that detail. This concludes the proof. Here's a small remark. So I'm going to let K be a finite abstract simplicial complex. From now on, when I say simplicial complex, I'm going to mean abstract simplicial complex. If I'm talking about geometric complexes, I'll make that explicit. But we're going to be working with abstract simplicial complexes more. So simplicial complex is just abstract simplicial complex. So the following is a result of Carl Menger. This is from the end of the 20th century. So he shows that if D is the maximum dimension of all the simplices in K, then K can be realized in RD to D plus 1. Right, so what he's saying is that what really determines the dimension in which you can realize your complex is really not the number of vertices as we did here, but rather the maximum dimension of the simplices, which actually makes a lot of sense. And let me give you an example as to why this is a tight bound. So for example, so let's say that I give you K, an abstract simplicial complex, which is essentially, do I need the complete graph? Perhaps I do. Let's do that. Right, so I'm going to let K be the abstract simplicial complex that has 5 vertices. It has all the edges between all the vertices. So the complete graph on 5 vertices. Okay. So this certainly has dimension 1, right? That's the size, the dimension, the highest dimension of a simplex in K is 1, but you cannot embed it in R2. So it cannot be realized in R2. So you really have to go to R3 to disentangle it, right? So the bound is sharp. Yep. Yeah. So what is the dimension of the complex? Is the dimension the highest dimension of a simplex in K. So let's see it here. This is made of 0 simplices and 1 simplices. So that's the largest dimension I have. Yeah. Okay. So this is a good time to reflect. So this is supposed to be a class about topology and data. The topology part is often presented as a very abstract component in pure mathematics. The data part is, as we hopefully know, is a very applied and useful part of computational mathematics and data science and so on. The particular style I like is a combination of the two. So we're gonna develop everything with a lot of care, right? We're gonna give definitions and theorems and make sure that things are constructed in a reasonable way. But in the end, these would be, I guess, not as useful if it didn't give you applications that you cared about. So that's where we're going. We're actually gonna code things up and apply it, okay? But we're gonna be careful in the meantime. So here is how perhaps this appears in data science, or at least in topological data analysis. This idea of geometric and abstract simplicial complex, yeah. Oh, because the triangles are not part of the complex. If I were to write this out explicitly, I would say is the vertices and the edges. So it's just the graph, the complete graph on 5 vertices. If I wanted to indicate that the two simplices were part of the complex, I would do this. Okay? Not a silly question at all. I was just not being completely clear. Okay? So here's the prototypical example that we're going to find in topological data analysis. So X is going to be a set. The set is going to be the data set. It's the collection of observations, right? So this can be vectors, they can be texts, they can be molecules, they can be time series. So X is the data set. In addition to the data set, I'm going to let rho from X cross X to 0, infinity be so that one rho xy is equal to 0 if and only if x is equal to y. And 2, I'm going to require that rho of x is equal to rho of y. So every time we have these two elements, I have a set and I have a function from x cross x to the non-negative reals, such that these two properties are satisfied. I'm going to call rho a distance. It's a distance between the points in X. So oftentimes when you're thinking about data science, one of the key points is how do you measure similarity or dissimilarity between your data points. If I gave you a collection of texts, then the question is how do you measure dissimilarity between text documents? How do you measure dissimilarity between genetic sequences? So this is key. If a third property is satisfied, so if the following is satisfied, so if rho xy, let's say xz, is less than or equal to xy plus yz, this is called the triangular inequality. for all x, y, and z in X, then X comma rho is called a metric space. Okay, so oftentimes we have a set with a distance function that is often enough to do data science, things like clustering and so on. But if you have things like the triangular inequality, that makes your life much, much easier. For example, it allows you to estimate the distance between a pair of points, knowing the distances between other points. So that is used in things like cover trees and finding nearest neighbors in metric spaces, okay, for large data sets. Yep. It is. So let me say the following. So if I just gave you a notion of the similarity, so what would be a good one? So the Manhattan, no, but that's an L, that's an L1, L infinity. No, that's right, that's right. So here's one distance. So say that you have two sequences, two genetic sequences, and you were to measure the percentage of overlap. How many things differ? Or you were to measure, let's say, the Pearson correlation. So those are notions of the similarity, but they do not satisfy, in general, the triangular inequality. Right? So they tell you how similar things are, but they don't respect this extra, more constrained structure. Okay, so, and yeah, where are we going with this? So, yeah, that's what I was going to say. Have you guys heard of the story of math professors? It worked for 40 minutes. Okay. So, yeah. So we're going to I'm going to continue with this. The example hasn't ended. I'm just sort of setting the idea of what an abstract data set is. So once we have that, if alpha is bigger than 0, so we're going to let our alpha of X, and perhaps rho, be the collection of sigmas inside of X, where this guy is finite and non-empty, such that the diameter of sigma is less than alpha. Where the diameter of sigma is the maximum is the maximum rho xy, where x comma y are in sigma. Okay, so it seems that I've pulled this definition out of nowhere, but we're going to see that it has a geometric meaning to it that we've already used. Okay. So the first thing I'm going to note is that this is actually an abstract simplicial complex. Okay. So what do you have to check? You have to check that it is a collection of finite non-empty sets that is already there by definition, and you have to check that it's closed under taking phases, right? So so let's say that you have sigma in here, and you take a phase, meaning a subset, right? If the diameter of these is less than alpha, then the diameter of any subset is certainly going to be less than alpha as well. Let me write that down. So indeed, if sigma is in R alpha X row, and tau is a non-empty subset of sigma, meaning a phase, then certainly the diameter of sigma is going to be bigger than the diameter of a smaller subset. Okay? Since this is in here, it means that this is in alpha. This is less than alpha, and therefore tau is also in here. Okay? So it is an abstract simplicial complex. We've checked the two properties we needed. So what have we done? We've shown that every time you give me a data set with a notion of distance, it doesn't have to be a metric. It doesn't have to satisfy the triangular inequality. You just have to be able to measure distances between points. Then I can build an abstract simplicial complex from it. And the fact that it's an abstract simplicial complex is this sort of 4-line argument over here. This is called the Rips complex. Let's see what the geometric intuition is. So what is the idea? The idea is that I have X, my data set, and here are the data points. Okay? And we fix a tolerance alpha. Okay? And I say every time a set has diameter less than alpha, I'm just going to consider it to be a simplex. So, I mean, this guy, yes, that is a useful thing to say. What is the diameter of, so let me do it this way. So let's say that X is an element of X. Okay? What is the diameter of this set? Is 0, correct? So it is certainly less than alpha, right? So in particular, all these guys are going to be vertices in the Rips complex, okay? Now, if 2 points are at a distance less than alpha, right, then I have an edge between them. And maybe that. And that in this. Okay? And if I have, let's say that this distance is less than alpha, this is less than alpha, and this is less than alpha, then the diameter of this set is also less than alpha. Correct? So that means that the 2 simplex is also there. I'm not adding them. I'm taking the maximum. The maximum distance, right? So for example, this is going to be a complete 3 simplex, right? So we've built a way of going from an abstract data set, thought of as a set with a distance, to an abstract simplicial complex, which we also know can be thought of as a geometric complex, if we wanted to. A lot of the sort of initial points in applied topology is thinking, how do you take a data set and then build geometric objects that are interesting out of them? And this gives you a way of doing that. Yep.
Then we will realize that what you mentioned.
Correct, correct. No doubt about that. So you have to be very careful, and this is true in any application, in any real application, right? You have to be careful about the choice of your metric, right? Or your distance rather, because this doesn't need to be a metric for this construction. Okay. Okay, great. Here's a question for the actual users, right? So if I give you a data set, how do you choose alpha? Right, so alpha should be sort of the scale at which I'm looking at my data set. If I just gave you a, any data set, what is a good alpha? Oh, that sounds very objective. I guess one answer is that there is no answer, right? There is no clear choice of alpha for a particular data set. So what we're going to do is think about what happens when we think of all the alphas at the same time, right? So again, for the people that are practitioners, is the difference between clustering and taking dendrograms. If those words mean anything to you, then fine, and if not, it's okay. We'll see right now what I mean by looking at all the alphas at the same time. So here's a remark. Notice that if alpha is less than or equal to alpha prime, then alpha x rho is a subset of alpha prime x rho. Right, because here I'm asking, give me all the things that have diameter less than alpha, then they certainly are going to have diameter less than alpha prime. Okay, so we have always this condition. Then I'm going to call this fancy R. It's going to be the collection of all the, and this is for alpha less than greater than 0. So each one of these guys gives you what is called, again, the Rips complex at scale alpha. As I change my alpha, I get this continence relation. So the thing that I'm going to get here in the end is called a filtration. So it is a filtration in the sense that I have all these complexes nested, contained into each other as I change my parameter alpha. And the game is going to be study what properties survive changes in alpha. Right? So instead of picking one single alpha that gives you everything you want, you look at all the alphas and try to look at things that are stable under changes in alpha. Okay? That's going to be the game. One advantage of this construction is that it gives you a very clean way of going from an abstract data set to a simplicial complex, something that has shape to it. It is very easy to compute. You just need pairwise distances. However, it tends to be very, very large, right? So, for example, when alpha goes to infinity, what is the size of this guy? Is the power set on X, right? So every single subset is going to be in there as alpha gets larger and larger and larger. So this grows very, very quickly. That's a problem. So I'm going to define another type of complex that is related to this guy and has better theoretical properties. here's a definition. So let X row be a metric space. So now I'm asking that we have the triangular inequality. And for alpha greater than 0, let B alpha X be the collection of points Y in X so that row XY is less than alpha. Okay, so this is the open ball of radius alpha centered at X. Right, the idea is that, you know, if this is X, and here's little x, then the ball of radius alpha is this. All the points that are at a distance less than an alpha. Then the Cech complex, so this is we just defined the Reeves complex, we're going to define another one. So the Cech complex is defined as at alpha of X. Let's put rho for good measure. So this is the collection of all the subsets of X, where this guy is finite and non-empty, so that the intersection of the balls of radius alpha centered at points in sigma is non-empty. Okay, so you take the collection of all the finite non-empty subsets of X, take them as centers of balls. So let's say that sigma is perhaps X0, X1, and X2. You look at their locations, you know, perhaps like that. You take balls of radius alpha around them. And then if there is a non-empty intersection, then that means that all of that this set will be an element of this guy. Okay. If I use the word complex, perhaps you can imagine that it's actually going to be a simplicial complex, and in fact it is. So the remark is that C alpha X rho is a simplicial complex. So I'm going to let you think about why that is the case. So that's the second exercise from the class. Think why this is actually a simplicial complex. So what do you have to check? You have to check that it's closed when you're taking phases. And hopefully that will be okay. Okay. So yeah, this is a good time to finish. So what have we done today? We started with this idea of measuring the shape of objects. It was either sort of surfaces, which we triangulated, or data sets, which we created sort of triangulated spaces around them. Then the entire class was spent defining this abstract notion of a simplicial complex, right? So we have the geometric picture, which requires coordinates in some Euclidean space, and we have the abstract picture, where you just have to give me the list of the simplices. And they are related by the fact that, you know, any finite abstract simplicial complex can be realized. And you can realize it, you know, in a large Euclidean space, for example, of the number of vertices, or you can just think about the largest dimension in the simplicial complex. And then we end with these two constructions, the Rips complex and the Cech complex. So on Monday, when we come back, I'll tell you a little bit more why this is a nice simplicial complex to think about. One downside is that this is harder to compute. And by compute, I mean algorithmically, right? So in a computer, it is harder to check, or more expensive to check this condition. In the Rips complex, it was actually pretty easy. It's just a matter of checking diameters. So checking distances is just pretty easy to do. This not so much. But this has other theoretical properties that are useful. Okay. Yeah, let's end for today. Have a good rest of the week, and I'll see you on Monday.